So now we get to the part of the class where we introduce one of the most important results in probability theory and statistical analysis, the central limit theorem. We're going to be using this result time and time again in what follows, so it's important to get a good sense of what it says. To put you in the right frame of mind, imagine the following situation. Professor has been teaching a course for the last 20 years. For every class during that period, the professor has recorded the midterm exam grades of all of the students that sat midterm. So we're going to have Xij be our random variables here, and they will be the grade that student I got on the midterm exam in year J. So presumably then there's a big list of a number of students and their grades. And the professor looks back on the class list and they find that the expectation for the random variable is 65 and the standard deviation is 15. Alright, so if you were to look at the entire distribution of grades over the 20 years, you get something that perhaps looks a little bit like this. And there's some spread here. In this year's class, there are 49 students. What should the professor expect of the class on average for the midterm examination? Well, the prof isn't sure what's going to happen, right? There could always be a year where the group will be different. Perhaps this is the year where all the gifted students are in the class. Or this is the year where everybody who's taken this class now has failed it in the previous year. Who knows? But in order to try to get a sense for what might happen, this is something they could do. They could simulate the results of the class of 49 students by generating a number of sample grades. So, they could do this m times, and every time they would generate 49 grades. But how will they generate these grades? They could draw them from a normal distribution set. So we assume that every year the grades are also normally distributed with mean 65 and standard deviation 15. So every year we have the following distribution. When we say that we're generating sample grades, what it means is that we pick 49 grades. This will be done randomly, and they will be picked in such a way that where the area is larger, there's a higher likelihood of picking a grade. Now, we would expect that these grades should be pretty close to 65, and in fact, it wouldn't be surprising to find out here that the expectation would be exactly 65, and that the sample mean of the things we've taken should be close to 65. So that's what we would expect from one generating sample. Now we could do this over and over and over again. So perhaps the first time we do this, we get a sample mean of 64. And then the second time we do it, we get a sample mean of 63. And the third time we do it, we get a sample mean of 65. Okay? Exactly the population. And the next time we do it, we got a funky sample, and this time the class average is 71. That could happen. In general, what you would expect to see is that most of these sample means should be close to 65. But what we'll also see is that they are close to 65, but they're actually much closer to 65 than what we get when we just look at the actual grades. So the averages have a tighter distribution. If I run these steps time and time again, tighter distribution than the distribution I get for the actual grades within each of the samples. So this would be potentially the distribution for all of the averages, and then the distribution for the grades might look like this, much wider compared to this. This property is what we mean when we refer to the central limit theorem. The more samples we take, the more sample means we compute, the tighter the distribution of the averages is, the more certain we are about the value of our estimation for the expectation. Formally, this is what the theorem says. But let's say that x bar is the mean of some random sample of size n, taken here from an unknown population. This population does not have to follow a normal distribution, even though in the previous example I assumed that the grades were normally distributed. This is going to work even if the underlying population of grades, say, is not normal. It could be an exponential distribution. It could be a gamma distribution. It could be any distribution. That distribution has mean mu and a finite variance. That part's important. It's got to be that when you compute the expectation of x minus the expectation of x squared, this has to be smaller than infinity. That very often happens with regular, reasonable distributions. So x bar is the mean of your random sample, and if you build a new variable z, which you obtain pretty much the same way you obtained the standard normal variable before, you will take the mean of the random sample. You will subtract from that the mean mu of the unknown population. You do know the mean. And you'll divide by sigma divided by the square root of the sample size. That quantity follows a standard normal distribution. Now, when you're working with the regular x, if you're not looking at the sample mean, but the actual values, remember that what we were saying is that this quantity follows a standard normal. That's what standardization is. Assuming, of course, that your x initially followed a normal distribution would mean mu and sigma squared. This isn't quite the same thing here. We're talking about the sample, not the actual values of the observations of the random variable, and we do divide by this extra term. Now, this is a limiting result. It's a standard normal approximately, and it's going to go to the standard normal when n goes to infinity, when the size of your sample gets larger and larger and larger. If you just look at the standardized ZNs here, so you're looking at the sample mean, if your sample is of size n, and you subtract from the sample mean, the mean of the population, you divide by sigma over square root of n as a function of n here, as a function of the sample size. It doesn't matter if the original xi's are normal or not. Right? What we have is that the probability that this standardized quantity is smaller than some threshold is approximately the same as phi at z. You'll remember that as the CDF, the standard normal distribution. This is part of the reason why we use normal distributions to model many situations, even if in practice it's not likely to be the case that a normal distribution is the best, most realistic assumption to make. What this is saying is that if you take large enough samples, the average, roughly speaking, behaves like a normal. Now, if you think about this a little bit more, you'll remember that the sample mean is a sum of values, and we divide that sum by the number of values, or if you'd want, you could also write this as saying that n times the sample mean is the sum of the observations. Well, what we've discovered here, or at least what the central limit theorem tells us, is that the sum of random variables is behaving like a multiple of the sample mean, and the sample mean behaves, roughly speaking, like a normal distribution. So the sum of the values that you obtain, the sum of the random variables, no matter what the random variable xi was. It could be an exponential, it could be a gamma, some of them could be exponentials, some of them could be gamma, some of them could be normals. When you add them all up and when n gets large enough, this sum behaves like a normal distribution. Here's an example. I am here plotting the histogram of the sum of one normal. So basically what I've done is I just generated values from a normal distribution. Here, a standard normal distribution. Great. These are just a bunch of x1s. Throughout, like all of my xi's are going to be standard normal distribution here, where I goes from 1 to, well, anything you want. In the second case, I have the sum of two normals. I am looking at x1 plus x2. And what I get from this is that if x1 is a standard normal and x2 is a standard normal, I would expect x1 plus x2 to also be a normal distribution with some standard deviation. The actual value here is not super important. Now you'll see that the range is a bit larger, right? Because I'm adding some larger values whenever I draw an x1 and an x2. But the sum is itself a normal. If I sum 5 normals, I also get a normal distribution. Centered at 0 with some standard deviation. And if I sum 25 of them, yet again, I get a normal distribution. Okay, so adding together the results of a bunch of normal values gives me a normal. The mean stays the same, but the spread, the dispersion, changes. We've mentioned that it wasn't important whether you started with a normal distribution or not, and I'm going to show you an example that illustrates that fact. Here, we're going to be adding exponential distributions. So all of my xi's follow some exponential distribution with a rate parameter lambda, some value of lambda. You could figure it out if you insisted on figuring. So if you do a histogram of some randomly selected exponentially distributed values, you would get a histogram that looks like a, well, what you would expect from an exponential distribution. Here I have x1 plus x2. Now, if x1 and x2 are exponential, x1 plus x2 does not follow an exponential necessarily. The fact that if x1 is normal and x2 is normal, the sum is normal, that's a property of normal distributions. But for exponentials, this isn't the case. So x1 plus x2 follows, well, what does it follow exactly? It's just a new distribution. I'm going to look here at x1 plus x2 plus x3 plus x4 plus x5. It still follows a new distribution. It is not looking very exponentially anymore, right? The exponential always sort of like goes down like this. There isn't going to be a turning point, so it's not very exponentially anymore. In fact, if you were to sum up 25 exponentials, you would have something which would approximately be a normal distribution for specific mu and sigma squared. If you look at this curve here, you get something which is, well, close to being normal. So you started with random variables that had nothing to do with normal distributions, and if you add enough of them, assuming of course that they're all independent, and that's an important point, they have to be independent of one another, but assuming that they're all independent, if you add enough of them, you get something that looks like a normal distribution. So because we don't know all of the details that go into experiments, whenever we run these experiments, we can control some aspects of experiments, but there's a bunch of things we can't control. There's a bunch of random variables in there that are hidden from us, hidden variables if you want. So we often make this assumption of normality, as I started saying earlier in the video, because since there's going to be a bunch of factors that are involved, if we assume that these factors are all independent from one another and they all go into creating the output of one run of the experiment. It's not completely far-fetched to assume that the total effect of all these things, roughly speaking, behaves like a normal distribution, assuming you have enough of it. Now, in many instances, this is still a very piss-poor approximation to make, and if you make that assumption when you're not supposed to make it, it's going to come back and burn you. But it is not completely ridiculous to make this assumption sometimes, even though it might not seem like a reasonable assumption to make. And that's due to the central limit theorem. Let's see if we can illustrate this with a slightly different example. So I'm back to my idea that you have a prof that has been teaching courses for years. And perhaps for the first assignment, the mean is 56 and the standard deviation is 11. So a different mean, a standard deviation. And the prof knows that this is the case because they've looked at years and years and years of results on that first assignment. So that mean of 56 and the standard deviation of 11, these are parameters of the distribution of actual grades. If I was to take any of you in this class and I was giving you that first assignment, I could expect you to get 56%, and I would expect there to be a standard deviation, some variation amongst all the grades, which would be 11. And this is something we've talked about how to compute before. So this is my population mean and my population standard deviation. And I've had enough students over the years say, well, I guess I'm the professor, but the professor has had enough students over the years to sort of trust that these results are like, the true results, the results that have settled over time. So now this year, let's assume that there are 49 students in the prof class. What's the probability that the average grade for that first assignment would be below 50? Knowing that the average grade in general is 56 and the standard deviation is 11. So now I'm asking a different question. I'm asking for the average of 49 grades. I'm interested in knowing how this quantity behaves. What I know is that each grade follows a distribution with mean 56 and standard deviation 11. That's all I know. And what distribution it is, well, that's not given. The prof knows what the mean distribution is and what the standard deviation is, but they don't know how the grades are actually distributed. Another question to ask, what's the probability that the average mark for the class, this time, the average in that class, would lie between 50 and 60? So we'll say that x1 all the way up to x49, these are the grades for the first assignment. And we assume that the performances are independent. So no cheating, no working with one another. Everybody comes at this completely independently. The sample mean, as I said, that's the sum of the 49 grades divided by 49. We know what the expectation of the mean is. It's 56. And when we talked about sampling distributions, we saw how to compute the variance of a sample mean, variance of a sum, and in this case this would be sigma squared divided by n, so 11 squared over 49. Now what this is telling us is if we're trying to compute the probability that x bar is smaller than 50, the probability that the class average for this year's class is smaller than 50, we're really computing the probability that x bar minus 56 would be smaller than 50 minus 56, right? Because these are the same intervals. And while we're at it, that would be the same thing as computing the probability of x bar minus 56 divided by 11 over 7, which is the square root of this thing here, would be smaller than 50 minus 56 divided by 11 over 7. So this thing here is the same as this. And that bit, x bar minus 56 divided by 11 over 7, well, it is the standardized value for the average. You'll notice here we are using the approximation. We cannot use equality because we do not know what the distribution of the grades are, right? We said that it followed the distribution with parameters mu and sigma. That's all we know about them. It's a distribution with mean mu and standard deviation sigma. So we have to keep this as an approximation, but the central limit theorem kicks in because n is large enough. I mean, n is big. It's not 2 or 3, it's 49. So the probability that the average is less than 50 would be about the same as the probability that the standard normal variable would be smaller than, well, the expression we got by n dividing by the square root of sigma squared divided by n, so 11 over 7. And if you work out this expression here, you'll get about minus 3.82. So the probability that the class average is less than 50 is about the same as the probability that the standard normal would be less than minus 3.82, and you will find in your tables for using R that this is a very small value, about 1/100th of 1%. They say that makes no sense, right? Because if the mean is 56 and the standard deviation is 11, there's going to be a bunch of students that get grades below 50. Easily 3 or 4, if not more. You're right, individual grades will fall below 50, but the average of 49 grades, it's very rarely going to fall below 50. If you know that the underlying grade distribution has mean 56 and standard deviation 11. The second question was to find the probability that the average would fall between 50 and 60. Again, given that the underlying distribution of grades had mean 56 and standard deviation 11. Well, you compute this probability by standardizing, or by using the standardization given by the central limit theorem. 50, 60, then the 56 comes from the mean, the 11 comes from sigma, and the 7 comes from the square root of n. And you can just work it out. That's going to be approximately the same as the probability that the standard normal would be between minus 3.82. We had computed this value before, it's the same, and 2.55. So in essence, what you're saying is that this is my standard normal, 0, here's my minus 3.82, here's my 2.55. The probability that the average of the grades will fall between 50 and 60 for that class of 49 students is about the same as the area under the standard normal CDF, under the standard normal PDF, between minus 3.82 and 2.55. So you just go out there and compute it. Phi at this extremity minus phi at this extremity, and you get very nearly 99.5% chance that the average will fall between 50 and 60. Now we saw in the previous slide that the probability of it being below 50 is very, very slim. The probability of the class average being between 50 and 60 is about 99.45%. If you add the 0.0001 we had for the probability of being smaller than 50, you'll end up with the probability that it's greater than 60 being approximately equal to 0.0004. Because we don't know if the underlying scores are normally distributed or not, we have to use the approximation. If they were normal, if the initial grades, the xi's, followed a normal distribution with mean 56 and standard deviation 11, or variance 11 squared, then all of these approximations would be inequalities. But n being 49 is probably large enough so that if there's a difference between the approximation and the real value, it's very, very slim. Let's look at another example. I don't know what systolic blood pressure is, but it's something you can measure in people. And let's say that we've tested a number of premenopausal, non-pregnant women between the ages of 35 and 40. We've done a bunch of them over the years, and we believe, we have strong indications to believe that the mean systolic blood pressure reading should be about 122.6, and a standard deviation should be about 11. Now, if you take an independent sample of 25 women from the target population, so premenopausal, not pregnant, ages 35 to 40, and you measure their blood pressure, what's the probability that the average blood pressure is going to be greater than 125? And do you think the answer would change if the sample size increased? Well, we use the central limit theorem. The average measurement should follow, or at least be close to following, a normal distribution with mean mu, 122.6, and variance sigma squared divided by n. So 11 squared divided by n25. So the probability that the average reading for these 25 women would be greater than 125, you would play the same game. You would standardize 125 minus mu, x bar minus mu, divide both sides by sigma divided by square root of n. That side on the left would become the standardized bit, and then you have the expression on the right that you have to evaluate, and this one evaluates to 1.09. So the probability that a cohort of 25 women would get an average systolic blood pressure higher than 125 would be approximately the same as the probability that the standard normal would be greater than 1.09. And if you remember, what this means is we are trying to compute this area here. Well, we compute the area by 1 minus the area which shows up here, and you're left with what's here. Use your tables, use R, you'll get about 14%. So it's not very likely that it would be greater than 125, but it's at least in the conversation. It could happen. If the sample size was 40 instead of being 25, what would happen? Well, everything would stay the same. The only quantity that would change here is this denominator. You wouldn't be dividing by the square root of 25, you'd be dividing by the square root of 40. And that gives you an overall smaller denominator, which means that this number here will be further to the right, which means that in general you would expect the area under the curve to be smaller. If you compute it, you will get that it's about 8%. That makes sense. Like, we would expect it to be smaller. By how much? That we have to compute the area under the curve to know. But it's not surprising that this value should be smaller. When you increase the sample size, remember you are reducing or restricting the width of the normal distribution that describes how the sample means behave. So the probability that the average in one cohort would be far from the expectation would be small, right? Large samples basically kill off or wash away the effect of outliers, odd results. You get closer and closer to the true results, the true proportion in the population. It's a little bit like election polling. If you take a small sample of 25 people, you might have gotten unlucky with your sample. It could be unrepresentative. But if you were to sample 1,000 people or 5,000 people, even if you were unlucky with a few people, you have such a large sample that there's a pretty good chance that you will have captured the real patterns, which is why bigger samples in polling, assuming that people have picked independently and that there isn't systematic undercounting or underrepresentation of certain elements in the population, would give you better results than small samples. Later we'll talk about confidence intervals. We'll have another way to quantify this property, that having more observations in your sample reduces the probability that your average or the quantity that you're trying to compute for the sample will be far from the actual expectation. And we'll do a last example here. Let's assume that you select 100 observations from a population with mean 5. That's the mu, and variance 0.01. That's sigma squared here. Here's your mu, here's your sigma squared. And n is 100. What's the probability that the difference between the sample mean of the random sample, so x bar, and the population mean, which is mu, exceeds 0.027? The only hard part about this question is actually figuring out what probability we're trying to compute. We need to translate that statement. What is the probability that the difference between the sample mean of the random sample and the mean of the population exceeds 0.027? It is this statement here. What's the probability that the absolute value of x bar minus mu, so the difference between x bar and mu, should be greater than 0.027? And once you've written that properly, you recognize that this can be expanded and written as either x bar minus mu is greater than 0.027 or mu minus x bar is greater than 0.027. But these two events here are mutually exclusive. They can't both happen, right? If x bar minus mu is greater than 0.027, then no, mu minus x bar is not going to be greater than 0.027, and vice versa. So because these are mutually exclusive events, the OR becomes a plus. We can separate the probability computation into two simpler probability computations. So we have the probability that x bar minus mu is greater than 0.27 plus the probability that mu minus x bar is greater than 0.027, and then you do the standardization. Once you've gotten to this point, you apply the central limit theorem on the central limit theorem standardized variable. So x bar minus mu, we already have an x bar minus mu, we're going to be happy with this, divided by sigma over square root of n. So this little bit here becomes this one, and then we have to do the same operations on the right hand side of the inequality. We don't need to subtract the mu here, because the mu is already subtracted on the left, right? Usually we subtract the mu on the left and on the right to put the expression here, the x, into the form z, but now we already have x bar minus mu. So all we need to add, modify, is the division, the denominator term here, plus the probability of the other one. So now if you want to have a term of the form x bar minus mu and you have mu minus x bar, you need to flip it, multiply by minus 1. So you're multiplying by minus 1 to get x bar minus mu, but if you multiply by minus 1, you multiply on both sides, and whenever you multiply by a negative number, the inequality has to change direction. You work it out. This thing will be the standardized variable for the central limit theorem for the average value. The expression on the right is 2.7. You do the same thing here. You work it out and you'll get, well, z smaller than minus 2.7. And in effect, what you're trying to compute is the area under the curve here. Well, they're both the same, right? I mean, because of symmetry of the standard normal, both of these quantities are the same. So you can compute each of them separately if you want. Or you can also just compute twice one of the areas. Either one of them will do. The computation in total, you'll get about 1%, 0.007. Okay, so the hard part really was to set up the probability that needed to be computed, and to remember that when you expand the absolute value, you get an OR statement, and the OR statement here presents you with two mutually exclusive alternatives. That means that the probability of the union will be the sum of the probabilities. And then you work it out the same way you work out all of these central limit theorem problems, by coming up with the appropriate standardization and making sure the terms on the other side of the equations give you what you want.